so far we covered basics of decision trees, like introduction to the structure of decision trees. We started with classification, and then we explained decision trees as type of classification. And we saw this structure. We know, for example, each income feature or attribute like that you have in your training set can help with predicting the outcome variable or your output feature, right? Or your class label. So let's start a review from here. So we just want to see this process with an example. So the main idea here is to divide and conquer. What do we mean by that? So we take the training test, which you see on the left, and you choose an attribute as your root attribute. So this is what is my focus for today's lecture. So I'm going to explain how we choose the best attribute as the root. And then from the root, we continue splitting and then deciding which is the next best attribute, which is the next best attribute, and so on. So before that, just the whole process is that you have this training set and you're choosing an attribute. So which are your input features here? Which attributes are your input features? Day, is that one of your input features? Yes, day, outlook, temperature, humidity, wind. Although day is not like really good predictor, right? But still, these are your input variables. And then the last column shows your class label, which are actually your predictions, right? Which are yes or no. Now, based on like this weather information and these attributes, we would like to decide whether we want to go play tennis or not. And so what is happening is that you're starting with some attributes, for example, outlook. Let's assume that we know the best attribute to start with is outlook. So at this point, we have 14 instances, right? So this is the whole data that we have. And so how many branches can we go from outlook? So the number of distinct values that exist in that feature, right? So outlook has 3 distinct values. So that are the number of branches that can go from here. Outlook, sunny, overcast, rainy. So out of those 14 instances of weather data, right, 5 of them goes into outlook sunny, right? Day 1, day 2, day 8, day 9, and day 11, right? So these are for outlook sunny. And then 4 days, 4 instances goes into outlook overcast, and 5 days goes into outlook rainy. Now we want to see, like after this step, we want to see whether we reach to the leaf or we need to further split based on other attributes. So for example, for outlook sunny, so we discussed several sub-conditions for our decision trees, right? One of the most important one is when all instances belong to the same class, right? For example, let's say you have 5 instances of outlook, for example, sunny, and they all belong to class yes. Do we need to further split on that? No, because we already know what is the prediction. So there is no point in further splitting the tree. So we reach to the no. There are other sub-conditions, like for example, if you reach to the end of your attribute, so you don't have any further attribute to split, right? So that is another sub-conditions, obviously. And what if, for example, you have no further attribute, but your instances are not belonging to the same class? So what do you do in that case? Which class label do you choose? The majority cases, right? So for example, let's say if 3 cases belong to class yes, 2 belongs to class no, then you use the majority, which is yes. And then finally, if there are no more instances or more examples in that sub-branch that you can continue on. So that's also another stopping condition. So for example, in one of your sub-branch, you may reach to the point where, for example, outlook is sunny, and let's say wind, for example, for wind can be, for example, a strong or weak, right? But they are, you don't have a strong wind in that subset at all, right? that is when you don't have any instances. So that is your third condition to stop. But if not, if that's not the case, you continue splitting, right? And that's the recursive process. So now for outlook sunny, should I continue or do we reach to the leaf node? So how many instances belong to class, have outlook sunny? 5 days, right? So do I reach to the leaf or should I continue splitting? Continue splitting, right? Because some of them belong to class no, right? Some of them belong to class yes. So they don't, not all of them belong to the same class, right? So these like here, can I actually draw here? Like for example here, right? So these are class no, right? And then here, for example, we have class no, but here we have class yes, right? So when you reach to the point where you have mixed class labels, you have to continue and choose the next best attribute. So again, let's assume we know that the next best attribute here is humidity, okay? So now we want to continue splitting or deciding whether we have to stop from here. So out of those days where outlook is sunny, which are only these 5 days, right? How many options do we have for humidity? So how many branches do we have if you want to split? How many branches do we have for humidity? How many distinct values do you have here? High, normal, right? So you only have the distinct values in humidity are high and normal, right? There are two branches, right? Now this could be, for example, humidity high. This could be humidity normal, right? Now, if outlook is sunny and humidity is high, which is, for example, outlook sunny here, humidity high here, again, outlook sunny, humidity high here, right? And here, these two are normal. So we only care about outlook sunny, humidity high. Do I reach to the leaf node or should I continue splitting? Leaf, right? Because they all belong to the same class. Because all of the cases where outlook is sunny and humidity is high, which are day 1, day 2, and day 8, right? Yeah, day 8, they all belong to class no. So this is no, right? And then the same thing for the other branches. So basically you have this, right? So for humidity high, you know that you reach to no because all these days belong to class no. And then for humidity normal, not only for humidity normal, but out of those 5 days where outlook is sunny and humidity is normal, right? Because humidity normal can happen like in many other places, but we care about those like 5 out of those 5 sunny days. How about outlook overcast? So how about outlook overcast? Should we continue splitting? Or do we reach to the leaf node again, right? Because outlook overcast is this one, right? This one and this one. So these 4. And they all belong to class yes. So as you see here, yes, yes, right? So they all belong to the same class. Again, this is the stop condition. So we reach to the leaf node, which is yes here. For outlook rainy, 5 days have outlook rainy. Out of those 5 days, do they all belong to the same class? Let's see. For example, here we have rainy, right? Some of them are yes, some of them are no. Again, here rainy is yes, and here rainy is no, right? So we have mixed class labels. So we have to further split. So let's say we assume that we know and we found what is the next best attribute, and that is wind. So you don't have to. I don't expect you to know it at this time. By the end of today's lecture, I expect you to know that, right? Why, for example, we have outlook here, why we have humidity here, and why we have wind here. So that is what I'm going to explain. So let's assume that we know that wind is the next best attribute here. And then out of, for example, those outlook rainy, out of those rainy days, that is day 4, 5, 6, 10, and 14, right? These 5 days. We want to see which days, for example, wind is strong, which is day 6 and 14, and which days wind is weak, which is day 4, 5, and 10, right? 4, 5, and 10. So these days, wind is weak. And because they all belong to the same class, that is, for example, when outlook is rainy and wind is strong, it's always prediction is no. It is don't go to play tennis, right? Because it's windy. But if it's rainy but the wind is weak, so they belong to class yes. So the prediction is that, okay, let's go play tennis. And so this is the whole process, right? Now there are several important points here. The first one is that when to declare, first of all, how to select the best attribute. That's what I'm going to explain. Second, when to declare no terminal. That is, you already know, right? We know we stop to the leaf node when there are no further attributes to split or no further instances or examples belonging to that branch, or if all examples belong to the same class, which means there is no point in further splitting the tree. So these are stopping conditions. And this part, how to select the best attribute, for example, for here, or for here, this I'm going to explain now. Now, how to select the best attribute? So ideally, we want to reach the position where we end up with like the purest splits. So we want to have the purest outcomes. What do I mean by pure? Do you recall that?
Plus minus v.
I'll explain. So what do I mean by pure? When all examples belong to the same class, is that pure? Yes. So now look here. We have 25 positive, 35 negative. What do they mean? Plus minus? That means 29 instances belong to class, for example, yes. 35 instances belong to class, no. So that was to answer your question. And then, which of these split do you think is better? Or any of them, do you think any of them resulted in a pure outcome? So what is a pure outcome? When all instances belong to the same class. Or at least like the majority of instances belong to the same class, which is not the case here. So except for the last one, where, for example, 11 cases belong to class positive, 2 negative. But still, there are lots of impurity here. So what is the ideal case? This is the ideal case. So where you have, for example, 29 positive in one branch, so all instances belong to class, for example, positive here and here, all examples belong to class negative. So this is the purest or the most ideal case. Now back to this one. So we said like none of these are actually resulted in like the pure outcome. And even though they are both started with the same, let's say, same data, they both have 29 positive, 35 negative, but they have different distributions, right? For example, this one distributed like this, 25, for example, positive here, 30 negative, for example, the other branch, and here another way. So after splitting, their distribution is different. And we want to see, for example, which attributes. So it's not always that easy to just look at attributes and find out which one is the best. For example, here, which one is the best? It's not really clear. So we will have to find a way to calculate or measure, right, which attribute is the best. So based on the concepts that we talked so far, we said we want to, like the ideal case is when the result is purer, right? So you have a pure outcome. So it's a good idea to find a measure, like to measure purity or impurity, right? Now, there are several selection criteria here, right? For example, like information gain, gain ratio, Gini index, and so on. The first three I'm going to explain in this course. And so I'm starting with information gain, which is based on a concept of entropy, which is actually a measure for calculating impurity. So let's see here. So the goal of information gain, the main objective is to finding which attribute we want to select at each level, right? So for example, should I select outlook? Should I select humidity? Or for example, wind, and so on. And then the attribute with the highest information gain is selected as a root node. Why? I'm going to explain when I'm explaining, for example, the formula of information gain. You better understand why the attribute with the highest information gain is selected. So information gain is reduction in entropy. So for example, if you want to calculate information gain of your training set, given attribute, for example, outlook, you have to see how much, if you're splitting, for example, based on outlook feature, how much this impurity or entropy is reduced. So in order to understand information gain, we have to know entropy, right? So let's first discuss entropy. So entropy is a measure that we use to, for example, in information theory and other fields, to measure impurity or chaos or confusion. For example, if, let's say, all examples belong to the same class, what is the impurity? What is the confusion? Zero. No confusion. We know like all of them belong to the same class. The prediction is clear, so there is zero confusion and zero impurity. Entropy is zero. So entropy zero is the ideal case because it means all examples belong to the same class. So the lower the entropy, right, the purer your outcome is. And so we say partition is pure if all tuples in it belong to the same class, right? And entropy is measuring impurity. So when entropy is high, it means impurity is high, right? So when entropy is high, impurity is high, confusion is high, so purity is less, right? And because purity is less, your information gain is also smaller. And you will also better realize it when I'm explaining more with the formula. So let's say you have a training set S, okay? So this is your training set. For example, that table including a weather data, that's your training set, okay? So that is S. And you have K classes. For example, 2 classes, playing tennis, yes or no, right? So those are also your classes. So K is 2, for example, here. So here is a formula for calculating entropy. Minus sigma K1 to K, PCI log of PCI. So here you can better understand. We can better understand everything. So this is the formula for entropy, right? Minus sigma K equal 1. Sorry. I equal to 1 to N or K or whatever. This is just anything you name it. It just means the number of classes that you have, right? And then you have PCI by log of PCI. So when we say when all instances belong to the same class, let's say you have 2 classes, okay? Class 1, class 2. And we say all examples belong to class 1. Let's say class 1 is, for example, play tennis. This is yes. This is showing no. If all examples belong to class yes, and PCI showing the class probabilities, that is probability of class 1, probability of class 2, probability of class I, right? So here we only have 2 classes. So we want to see what is probability of class 1 and what is probability of class 2. So if all instances or all examples belong to class 1, what is the probability?
1.
1. What is the probability of other classes? 0. Because like 100% they all go into this class. So even if you had more classes, these were all 0, right? Now why entropy will be 0? Because entropy is minus, right? Sigma PCI multiplied by log of PCI. So what is your PC1? 1, right? Multiplied by log of 1. What is this? What is log of 1? 0, right? 2 to the power of 0 is 1. So this is 1. And then the rest is also 0, right? because PC2, or even if you have more PCs, right, more classes, they are still 0, right? So this will be 0. And that's why when all instances belong to the same class, when you have the maximum purity, entropy is 0, right? And this is the minimum amount for the entropy. Now, what if we have, for example, 2 classes, and half instances belong to class 1, half instances belong to class 2? What would be the entropy? So if half of the instances belong to class 1, what is the probability of class 1? Right? The same for PC2, right? 50% goes into this class, 50% goes into this class. So the probabilities are the same. Now, the entropy of this set would be minus 1 over 2 by log of 1 over 2, right? Minus the same. Now, what is this? Minus 1, right? Because 2 to the power of minus 1 is equal to this, right? This is like 2 to the power of minus k is 1 to 2 to the power of k, right? So here we have minus 1. So this is minus 1. So we have minus 1 over 2 multiplied by minus 1, which is 1 over 2 plus 1 over 2, which is 1. So if like the maximum impurity is when you have, for example, let's say 2 classes, half instances belong to one class, half instances belong to the other class, right? That's the maximum confusion and impurity. And that's when your entropy is the highest, which is 1. So now, I have a question. Why do we have a minus here? Why are we using minus in this formula? Yeah.
I think because when we calculate probability, it's between 0 and 1. So if we do log of something, then it would be a negative number. So.
Yep. So, like, what is entropy? It's a measure of impurity, right? So this, we cannot have like a measure of impurity that is negative, right? So it should be a positive number. But the problem is that your probabilities will be between 0 and 1, right? So the minimum is what we calculated before, when your class is the purest, right? When all instances belong to the same class. So in that case, entropy is 0. If impurity is the highest, which means, for example, half instances belong to one class, half instances belong to the other class, then impurity is the highest, right? And so entropy is 1. So your entropy values will fall between 0 to 1, right? So what are the log of any number that is between 0 and 1? A negative number, right? Because of this reason. So they are all negative numbers. And because we want to get rid of that, just to provide a meaning for our measure, right? So we add this minus here. Should you know this or should you memorize this? No. You can like bring cheat sheet at your exam, have like this formula. So why I'm explaining this? Because I hate you memorizing this. I just want you to understand why things are happening, and that will be more sweet when you learn, right? So you know what is happening, why you have minus here, why, for example, when entropy, like when all instances belong to the same class, entropy is 0. If it is half, why it is 1. So they all just make sense. And so suppose you have 9 examples in class 1, 5 examples in class 2. So what would be the entropy? Easy, right? So that would be minus sigma PCI multiplied by log of PCI, right? So we said 9 examples belong, let's say, to class positive. 6 examples belong to class negative. Or I don't know how many examples. Let's say 9 and 4. So what would be the entropy? If you have 9 and 4, right? So the total is 13, right? So you would have minus, and then you have, instead of 1 over 2, you have, for example, 9 over 13. In our case, like in the example in the slide, we had 14 days, right? So here you would have like had 14, right? 9 out of 14 by log of that minus the rest, which is 5 over 14 log of 5 over 14. And then you calculate it using your calculator. But please be careful. If you're given a tree, when you're building your tree, so for example, if you have, and it happens a lot, for example, you see you have a branch like overcast. All examples belong to class, for example, yes or no, so they all belong to the same class. You don't have to calculate entropy, right? We already mentioned that's 0 and why it is 0. You already know that, right? Because in that case, the log of 0 would be 1, right? But the PCI are all zeros. And then the same thing, if, for example, you have half examples, let's say you have 4 days that are rainy. Out of 4 days that are rainy, if 2 of them belong to class yes, 2 of them belong to class no. That is, if 2 of them have class label yes, 2 of them have class label no, should you calculate entropy? No. What is the entropy? 1, right? Because of this reason. Because then half examples belong to class 1, right? Would be 1 over 2 log of 1 over 2. Minus, again, the other half belongs to the other class, which means this. And then log of 1 over 2 is minus 1. So you get this value, which is 1. And so the same way you, for example, calculate this here, if all examples are uniformly distributed in 3 classes, then we have, for example, minus 1 over 3 log of 1 over 3, again, minus 1 over 3 log of 1 over 3, and so on. That's why we just multiply by 3 here. And then we also learned about methods to split test conditions. Depends on the type of attribute. We discussed several attributes such as nominal, ordinal, continuous, and also how we can split them like binary or multi-way. So I'm going to go over them quickly because I already explained them last session. If they are nominal, no issues, right? Nominal attribute are categorical attribute with no order, such as marital status, color, anything like that without order. If you want to do multi-way split, it's like this, right? So you create one branch for every distinct value. Like, for example, weather can be sunny, overcast, rainy. Marital status could be single, divorced, married. Now, what if you want to do this, which has, for example, 3 distinct values, but you want to do a binary split? No problem, you can do it. So you put, for example, single in one branch, anything that is not single, for example, married and divorced in the other. Or, for example, married, single, divorced in the other. So all of these, all of them are okay. Now, what if you have an ordinal attribute? The same thing. So in this case, because our attributes have orders, right? For example, small, medium, large, extra large for the attribute shared size, right? So these are the acceptable binary splits. For example, a small, medium in one branch, large, extra large in another branch. A small in one branch, medium, large, extra large in another branch. But this one, this is not allowed, right? Because it doesn't preserve the order. And then for continuous attributes, we just choose the threshold. Like, for example, if we have salary, then we can choose the threshold like 80K. Then if outcome is, for example, greater than 80K, if income is greater than 80K or less than 80K, that's a binary split. Or we can just create like these different categories, right? And we also talked about discretization and binary decision for continuous attributes. So the ways that we can handle continuous attributes in general is that you either want to convert them to categories, like you use discretization to convert them to categories. For example, if you just have income, instead of keeping income like 100K, 100, 260, and so on, you just care about whether income is low, medium, high, something like that. So you use discretization for that purpose. Or maybe you have a binary decision, right? So In this case, you choose a threshold, right? For example, 80K, 100K. And then you have, for example, income less than that number or greater than. So this consider all possible splits. So it tries many thresholds to choose the best one. And so it is the most accurate one, but also the most expensive one. And I hope you recall this example we explained, right? Here, half examples belong to class 0, half examples belong to class 1. And then we have like these these 4 income features. And in this example, we used, for example, 3 different attributes to choose for splitting, right? And we want to decide which one is the best. So we started, for example, with gender. So gender, for example, let's say this is male. So yes, it's male. And this is female. So here, for example, we have 6 male belonging to class 0, 4 male belonging to class 1, right? So that is why you see C06 here, C14. And here is for female. So out of, for example, 10 cases that are female, 4 of them belong to class 0, right? And then the other 6 belong to class 1. This is what you see here, right? Is this a good split? Why not?
High entropy.
High entropy, right? What does it mean, high entropy? High impurity, right? Do we have pure, like even by looking at this, we know that this is not the best split because it didn't cause like, if it was a good split, we would see something like at least most cases belong to the same class, even if not all cases belong to the same class, but at least most of them. Like for example, this example here, like with car type, let's see, for example, the family branch. 3 examples belong to class 1, only 1 belongs to class 0. Again, sports branch. All examples, this is like the purest, right? All examples belong to class 0, and we have no instances belonging to the other class. So that one entropy is 0 for that branch. And then for luxury, again, entropy is very close to 0 because 7 instances out of 8 belong to one class. So this is a better split. This is better compared to gender. So far we know that this is not the best. Now between car type and customer, only if you consider entropy, which one results in like the purest results? Which one is better?
Customer ID.
Customer ID, obviously, giving you the purest branches, right? So this one, because like it literally creates one branch for every distinct values of customer ID. So when you only have one instance, right, in each branch, it means all instances of that branch goes into one class because it only has one instance. So these are the purest. But this is not the best split. It's not informative, right? You cannot generalize on this. So it's not a good one for prediction. And this is one of the actually limitations of information gain when I'm explaining, because information gain is only based on entropy. Entropy cares only about purity and impurity, right? So if you end up with like some split like customer ID, or for example, in our weather data, if you split on day, right, you have 14 days, D1 to D14, and they're all distinct values, right? So if you want to split based on day, and if you calculate information gain for day, temperature, outlook, wind, and humidity, you will get the highest information gain for day because it has entropy of 0, right? It has like the purest outcome. But is it the best one for splitting? Obviously no. So we have to be careful with that. And that's why we need to also introduce other measures after information gain, which I hopefully can find time to do it today. But let's focus on information gain for now. So this is also not the good one. So this is, even though this is not the ideal split, but it is giving us like a closest, I think, between like these, giving us the closest one to the ideal case. Now, how to determine the best split? We use a greedy approach. What do you mean by greedy approach? It means that at each node, You only care about the best attribute at that level. And that's it. So at each node, you just make a local decision and you choose a split that looks best right now. So nodes that have, like, for example, that end with the result in purer results, those are the best options. So to do this, we need to measure purity, right? So let's look at these two examples. Which one has highest purity? Right? Which one has highest purity? This one, right? This is not. What is the entropy of this one? 5 examples belong to class 0. 5 examples belong to class 1. What is the entropy? 1, right? Because half examples belong to class 1. It means PC1 is 1 over 2. 50% goes into this class. 50% goes into this class. So what would be the entropy? Minus 1 over 2 log of 1 over 2, right? Minus 1 over 2 log of 1 over 2. And this will be minus 1, right? And this is 1. So this is also minus 1, right? So this is obviously entropy here is 1. So this is the maximum impurity, right? And this should give us something close to 0, right? Because most instances belong to one class, which is class 0 here. Now, what is information gain? So what is information gain? As I mentioned before, it is one of the measures that I'm going to explain and I'm going to introduce in this course that we use to help us choose the best attribute in decision trees at each level. For example, at the root level, next level, and so on. So used to choose an attribute to split a data. For example, if you use information gain, you can decide, for example, based on the weather data, whether you have to choose outlook as a root node, or temperature, or humidity, and so on. So what is the formula? So assuming, for example, you have a set S, which is your training set, that data set that we had, for example, for the weather data. In that case, if you choose, for example, if you assume that attribute A, if you want to split S based on A, and let's say A is outlook. So let's say your S is your training set. For example, the weather data that I shared in my slide, right? And then A is, for example, outlook. A could be actually any of those attributes. Like, let's say it's outlook, then what would be M? What would be M? Wake up. Yeah?
Number of attributes?
Yeah, number of?
Like the attributes or the conditions.
Number of distinct values in that attribute, right? So assume that attribute A has M values, right? That means outlook has 3 values, right? Sunny, overcast, rainy, right? And that's why if you split on A, which is outlook, right? This is your A, right? It will give you M branches, 1 to M branches. Here, 3 branches, right? 1 is for this value, which is sunny. 1 is for overcast. 1 is for rainy, right? And then based on this, you continue. For example, you say, okay, here we have 14 days, 14 instances. Out of these 14 instances, we know, for example, how many of them belong to class yes, how many belong to class no. And then, for example, 5 of them goes into sunny because out of 14 days, 5 days are sunny. Now we have to see out of 5 days that are sunny, how many of them belong to class yes, how many belong to class no. For instance, if we have 2 days belong to class yes, 3 days belong to class no, that's how we show it. So that positive and negative, plus and minus means belonging to class yes, no, right? Now, back to the formula for information gain. So we say gain of set, so our training set, given A, given attribute A, for example, outlook, is expected reduction in entropy due to partitioning S on attribute A. So basically, we said we want to end up with purer outcomes, right? So we want to choose the attribute that create a splits in a way that we end up with purer nodes. What does that mean? It means that we want to reduce impurity as much as we can. How can we measure that reduction in impurity? Using information gain. So you have to measure impurity of the original set, right? And what would that be? How can you measure the impurity of original set? Come on. How do you measure impurity? Entropy, right? So entropy gives you that. So you measure entropy. So entropy of S, this gives you impurity of original set, right? Now, how can we measure how much we can reduce impurity? So you have to, for example, let's say if you choose an attribute A, for example, outlook, right? It means if you want to choose outlook here, right? And you have some entropy here, which is entropy of your original set. For example, 0.9, okay? So you measure entropy at this point for the whole set, and that's 0.9. So what should you do? You have to measure also the entropy of, like, each of these splits or branches, right? Each of these subsets, for example, for subset sunny, overcast, rainy. So you measure entropy for each of these as well. So you measure entropy here, entropy here, entropy here. And then you sum them, right? You also calculate the sum because you want to see how much impurity does this one cause. And then you deduct it from the entropy S, which is the impurity of the original set, so that you find out what was the reduction in impurity, right? So the more we can reduce impurity, it means we are resulting in purer sets, right? If we are resulting in like purer outcome, that's what we want, right? Now, gain or information gain of S given attribute A is entropy of your original set minus sum of weighted average entropes of like each of these subsets. So this is the weight of the ith partition. And so as I said, for example, if you have an attribute A such as outlook, so you want to see what was the entropy of the set at the beginning. And then you want to also find out what are the entropies of, for example, if you choose this attribute to split, right? What is the entropy or impurity based on each of like those branches that this attribute cause? For example, sunny, overcast, rainy. And why do we consider weighted average entropy? Why do we consider weights?
The representation is proportional.
Sorry?
The representation is proportional. Just for each branch you create from the original node, you want to give each representation its weight, compared to the original set. That's why you have to weight there.
Yeah, we want the branches with more instances weight more, right? So we want the larger subsets matter more compared to smaller subsets. That's why you're adding these weights here. So we just weight like these entropy of the subsets by their size, right? Because not all subsets have the same size, right? For example, we may have 5 examples here, 2 examples here, 8 examples here, right? So we want to weight them. And so this will give us the expected reduction in entropy, right? So you have to calculate the entropy of the original set and then also the weighted average entropy of the subsets, right? And then deduct it from the whole entropy. This gives you information gain. So let's see it with an example to better understand what is happening here. So this is our training example. So this is your set S. So at first, we want to choose which of these attributes we want to choose. So basically, we know that we do not care about day because it has many distinct values. It gives us the highest purity, but it doesn't give us, like, it's not informative, right? But out of, for example, outlook, temperature, humidity, and wind, which one to choose here as the root node, right? This is what we want to decide. So we have to calculate information gain for outlook, information gain for temperature, information gain for humidity, information gain for wind. This is what decision trees are doing. So we have to calculate information gain. So for example, outlook, gain of, so let's call it gain of S given outlook, S given temperature, gain of S given, humidity, gain of S given wind. And for each of these, we need to find out entropies of all the subsets and deduct it from the entropy of the original set. So you have to start with entropy of the original set. What is the entropy of original set? So let's calculate entropy of S first. So I'm going to do it here. What is the entropy of S here in this example? Entropy minus sigma PCI log PCI, right? Class probabilities multiplied by their log, right? So it will be minus. So out of 14 examples that we have here, how many of them belong to class yes? Okay, let's count. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 positive, right? And the rest are negative. So we have also 5 class no, right? So we have 9 plus and 5 no. So the entropy of the whole set would be minus 9 out of 14 log of this, right? Minus 514 log of 514, right? And this gives you some number. I don't know. I didn't memorize this. Some number here, right? You can like calculate it using your calculator in the exam. Now, we know the entropy of the original set, and we want to see which attribute we want to choose. So let's calculate information gain of our set given, for example, outlook first. We already calculated entropy of S. We know that this is entropy of S minus sigma, right? And here you have the weighted, right? The weighted average entropies, right? You have entropy of your subsets here, right? Now, for the outlook, what are the subsets? Sunny, overcast, rainy. So you have to calculate entropies here. And then you also have to weight them. So what would be the entropy of outlook sunny? What is entropy? Always remember, entropy cares about class labels. Why? Because entropy measures impurity. Purity means all instances belong to the same class. So we care about how many instances belong to each class, right? So please remember, why do I focus on this and why do I emphasize? Because later you will have very similar formula, and I don't want you to, and it's very similar to entropy, and I don't want you to confuse them. So it's important that you understand this rather than just memorizing this. So entropy is a measure of impurity, which means we care about how many instances belong to class yes, how many belongs to class no. So here, for outlook sunny, let me be like a bit cleaner here. So here we have output, and we have some entropy here. Entropy S is something. We have sunny here. We have overcast here. And we have rainy here. What is entropy of outlook sunny? What is this? First, how many instances are sunny? Out of 14 days, how many are sunny? 5 days. Now we have 5 days. How many of them? So entropy cares about class labels. So we need to know how many belongs to class yes, how many belongs to class no. Why? Because if all 5 days belongs, let's say, to class yes, it means entropy is 0, right? So, like, are all 5 instances where outlook is sunny belong to the same class? No. 3 of them belongs to class no, right? So 3 negative. So negative here, this minus plus, this means 3 examples or 3 instances belong to class no. And 2 of them belongs to class yes. So out of 5 examples or instances that goes into this branch, 3 of them are negative, belong to class negative. 2 of them belong to class positive. So what would be the entropy?
Negative 2 by 5.
Yeah. So the entropy would be, again, you use the same formula, right? PCI multiplied by log of PCI. What are the class probabilities here? 3 over 5, log of 3 over 5, right? And then minus 2 over 5, log of 2 over 5. So see here, I think this is more clear. So here in a slide, I started with humidity. Doesn't matter. Like, you have to check all 4 attributes. So it doesn't matter you start with outlook, temperature, or whatever attributes. You have to calculate information gain for all of them to see which one is the best. So for example, for humidity has 2 distinct values. So it goes into these 2 branches. Could be high or normal, right? And this is the original set entropy. So this is the entropy of the original set. So we started with 9 examples belong to class positive, 5 examples belong to class negative. And this was the entropy of the original set, which we calculated there, right? And then out of like these examples, how many of them belong to, for example, humidity high? So out of 14 examples, how many of them have humidity high?
7.
So go here, right? So you want to see how many of them have humidity high? 1, 2, 3, 4, 5, 6, 7, right? So we have 7 instances where humidity is high. So when you go here for humidity high and you want to calculate entropy here, and you have 7 instances, what do you care for entropy? How many of those 7 instances belong to class yes? How many belong to class no, right? So out of those 7 cases, which are here, let's see how many belong to, for example, class yes. So for example, humidity high is here, but class label is no. And then we have, for example, humidity high here, belong to class yes, right? Again, humidity high belongs to class no. Sorry, this should be green. So this is class no. Okay, this is class no. And humidity high, again, class no, right? So 1, 2, 3 of them belong to class no. And 4 of them belong to class, 1. Actually, this one was also no. So this is also humidity high, right? With class label no. So 1, 2 here, 3 here, and 4 instances belong to class no. And then for class yes, we have high yes here, 1, 2 here, And then another one here. And then another one here where this is high and class label is yes. 3 of them belong to class yes, right? So we care about how many belong to class no, how many belong to class yes. So as you see here, humidity high have 7 instances. Out of those 7 instances, 3 of them belong to class yes, 4 of them belong to class no. So the entropy is this number. How did we calculate entropy? So this is, how did you measure entropy here? How did I reach to that number? So for temperature, this is for humidity, right? Which could be high or normal. Now for humidity high, we have 7 instances. 3 of them belong to class yes, 4 belong to class no. So entropy for high, entropy of humidity high, this subset, that is this one, if you start from humidity, if this is your root, you will have this. So this is high, this is normal. Now you have 3 plus 4 minus here, right? And the entropy would be minus 3 over 7, right? Not over 14. We are not considering the whole set anymore. This is the entropy of the subset. So this is minus 3 over 7, log of 3 over 7, minus 4 over 7, log of 4 over 7. And this gives us some number, right? Which is this number. And then we do the same for humidity normal. So we have 7 days where humidity is normal. Out of those 7 days where humidity is normal, if you check your training set, and I'm not going back to the training set again, but please check it yourself. If you go check that, 6 of them belong to class yes, 1 belong to class no. So the entropy for this branch, for this subset, would be minus 6 over 7 log of 6 over 7 minus 1 over 7 log of 1 over 7, right? And this gives you this number here. Even by looking at these two, you know that you should end up with a lower entropy in this branch. Yes? Am I correct? Yeah. You have a purer split here. Here you, like out of 7 cases, majority of them belong to class yes. 6 out of 7 belong to class yes. So the entropy will be less than this one. Here it's like totally mixed. So you continue the same way. And so you do it for all branches. You calculate entropy of the subsets. And then what would be the gain of S given humidity? So gain of S given humidity would be the entropy of the original set, right, which is this number, minus sum of the weighted, like average entropies. So here the only important thing is that we already calculated these entropies, right? So this is, for example, here, calculated here. And this entropy is also for this branch, which is calculated here. But you have to make sure that you also apply the weights, right? 7 out of 14 instances belong to this branch. 7 out of 14 instances belong to this branch. Because at the beginning, we had 14 days, right? 7 days, humidity is high. 7 days, humidity is normal. And the same thing is for outlook. So if you look outlook, again, you start with the same entropy here, right? Because this is the entropy of the original set. It's always minus 9 over 15 log of 9 over 15, minus 5 over 14 log of 5 over 14, right? That is the entropy of the whole set. Now, if you go over this one, let's see what would be the information gain. So you have to calculate the weighted average entropy of the subsets. Let's do it for sunny. Out of 14 days, 5 days are sunny. Out of 5 days which are sunny, 2 of them belong to class yes, 3 of them belong to class no. what would be the entropy? Entropy would be minus 2 over 5 log of 2 over 5 minus 3 over 5 log of 3 over 5. Right? So this is how you reach this number. And then the same thing for overcast. Should we calculate it here? No, because you see 4 out of 4 instances where outlook is overcast, they all belong to class yes, so entropy is 0. For rainy, should we calculate it? Again, no, because you have 2 positive, 3 negative here. It's the same mix here, 3 positive, 2 negative, but it doesn't matter, right? Because again, it will be the same calculation. So you don't need actually to calculate it again. Now, what would be the gain of S given this attribute? It will be the entropy of the original set, which is the impurity of your original set, minus like the weighted average of entropy of the subsets. So we have entropy of the subsets, and you have to like basically just see here, for example, for outlook sunny for this branch, where this is the entropy, how like what proportion of data goes into that branch? 5 over 14. And that's why you multiply by 5 over 14. Here you multiply by 4 over 14 because 4 out of 14 instances goes into this branch. So basically we want to put more weight, or like we want the branches with more instances matter more. So far, this is the highest. And now if you continue with the like the other 2 attributes, so the same thing here and here, sorry. So you will end up like with these numbers, and then you select the highest one as your root level. So this will be your root level. Now, when you continue from here, let's say, for example, when you go to the branch sunny, the only thing that you have to take care is that now, like from here to like the next. So I just put here because the entropy is 0, so we know that we reach to the leaf. But now, let's say we want to see what is the next best attribute after outlook sunny. So for this branch, so specifically this branch, what would be the best? Is it temperature? Is it humidity or what? So how do we do it? You have to calculate gain of S. But what is your S now? Your S is this one now, right? Because now you want to go one level later. You're already in this branch where outlook is sunny. So your set now only have 5 days, right? So you want to calculate gain of S sunny given humidity, gain of S sunny given temperature, and gain of S sunny given wind. So please remember not to put the entropy of the original set here. So here, your original set in next level, which we are here, your original set here is S sunny, right? Because you started from here. So you have to put entropy of S sunny here. And then you see, okay, if you are selecting humidity here, so if you are selecting humidity here, then you see, for example, what would be the entropy of humidity, for example, high and normal based on this branch. And it seems that all instances belong to the same class and entropies are 0. So these numbers will be 0. And then you select these numbers. So again, similar process. You choose an attribute with the highest information gain, which in this case is humidity, right? And that's the whole thing that you do for everything. So as you see, we reach to the leaf here because all instances belong to class no. Here, all instances belong to class yes. And that's why in the previous slide, you see 0, 0 here for entropies, right? Because we reach to the point where all instances belong to the same class, like this one, right? Where entropy is 0. So entropy here is 0. Entropy here is 0, right? We reach to the leaf node. And we choose the same method to choose the best next attribute for the outlook. So for example, between wind and temperature, you can, for example, other attributes, whatever attribute that you have, again, you can choose the next best based on, for example, the information gain that you calculate. And this is just showing the whole algorithm that you start with selecting the best attribute for the root. then you continue splitting. If you reach the stopping conditions that you see here, which means if all examples belong to the same class, if you have no further attribute to split, if you have no further instances or examples to include in that branch, then you stop. If not, if you still have features, if still you have mixed, for example, outcomes, then you continue splitting until you reach the leaf. So this is the recursive process. And that's it. Do you have any question? I'm going to explain gain ratio next session. Yep. Okay, do you have any questions? No question? Okay. Have a great evening.